is Dr. Back, and I'm going to talk to you about lattice energy in today's video. One of the major themes in chemistry is energy. We've seen energy in several forms already, and most recently we saw this in the form of ionization energy. So how much energy does it take to take one electron off of an atom to make it into an ion? And ionization energy and energy that we look at today is going to be based primarily or solely upon the energy that comes from having two charges that are close to each other. And this can be represented in Coulomb's law. The Coulomb's law describes the interaction between these two charges, Q1 and Q2, and the distance that exists between those two charges, in this case d squared. And you multiply it by some constant k, and you get some force that holds those two charges together or repels them apart if they're the same charge. And the beautiful thing about Coulomb's law is that it describes everything that you really need to know to be able to suss out what will be the behaviors of ionic charges and ionic compounds. And we're going to use this today. So the whole point of this is to be able to make predictions using Coulomb's law. And these two things from Coulomb's law, one is the charge and two is the distance. You'll use the charge and the distance to be able to make predictions about how ionic compounds will behave. Okay, so as a reminder about ionic compounds. So we take sodium and we remove an electron to chlorine, and we have sodium ion and a chlorine ion. And this will pack together into a solid that looks something like this, representing the blue or purple being representative of the sodium ions and green being representative of the chlorine ions. And they'll pack together in such a way that you have as many of the positive charges surrounding each of the negative charges. And vice versa, you try to have as many of the negative charges surrounded by positive charges. As many interactions between positive and negative as possible. All right. So before we talked about this ionization energy, so this blue arrow here, removing the electron from sodium. How much energy does it take to remove an electron from sodium? Okay, well, let's look at sodium. So what happens when we take our sodium chloride and we put that into water? We have our sodium chlorine, our solid sodium chloride in its nice crystal structure. We put it into water, and of course it dissociates. And this is one of the benefits of ionic compounds. They dissociate in water. Here we'll separate it into its component ions. And this has some characteristics that are useful to us, such as being able to conduct electricity. If we had put a thermometer into this, we would have observed that as we put the salt into the water, the temperature of the water decreased. Now thinking back to how energy behaves, that if we have energy moving from water, it has to go someplace. And where did it go? Well, it went into breaking apart all of those sodium and chlorine interactions that existed in the ionic solid. So breaking apart those ionic bonds is going to take some energy. We can represent this, or we can get some hint at what this might be by looking at how sodium chloride dissolves in water. But this is a little more complex. There are other things going on there. We have water-water bonds being broken, water ion bonds being formed. So we'll try to clean it up a little bit. And our clean way of looking at this is going to be lattice energy. Lattice energy is defined as the energy required to completely separate a mole of solid ionic compound into its gaseous phases. So we're taking all these ions that are interacting with each other in a solid form, and we're separating them as far apart as possible. So in a gas, there's no interactions between atoms or molecules. And we've separated these entirely. So all of the energy that it takes to separate these is what we define as lattice energy. Its energy, we can represent it in several different ways. One convenient way to represent it is with enthalpy. So we can write a reaction, in this case sodium chloride solid, turn it into sodium ion and chlorine ion that are in a gas phase. And this happens to take up 788 kilojoules. So the amount of energy that it takes to separate these and put them into different phases. Okay, the purpose of this is to be able to make predictions. So we want to be able to predict how much energy is it going to take, or what's going to have more energy, which will take more energy to remove. Let's try a few. So looking at lithium fluoride or lithium iodide, which one will take more energy to separate? Which one will have greater lattice energy? Which one will take more energy to separate into its individual ions? Remember, there are two things that have an effect here. So according to Coulomb's law, the only thing that has an effect are going to be the charge, the amount of charge, and the distance between those two charges. Well, let's look at this. Lithium and fluorine. Lithium is +1, fluorine is -1. And lithium iodide, they have the same charges. Lithium is still +1, and iodine is going to be -1, same as fluorine. There's no difference in charges there, so it's hard to make any prediction. Well, let's look at ionic radius. So lithium is not going to change, but fluorine is going to be much smaller than iodine. Even the fluorine ion will be much smaller than the iodine ion. So this means that fluorine charge, the charge in fluorine, is going to be closer to the lithium than the charge in ion. And according to Coulomb's law, the shorter the distance, the greater the interaction, the stronger the interaction. So we predict that lithium fluoride is going to be closer together, have a stronger charge interaction, and it'll take more energy to break that interaction, so have a higher lattice energy. So one way to look at this diagrammatically is to be able to see the fluorine ion is smaller, my radius, my distance between the center of the lithium and the center of the fluorine atom is smaller than the distance between the center of the lithium and the center of the iodine atom. Therefore, my lattice energy is going to be greater due to the stronger interactions we can predict from Coulomb's charge. Okay, let's look at another one. So magnesium chloride versus magnesium oxide. So here the radiuses are very similar, but the charges are different. So chlorine is going to be -1, oxygen is going to be -2. Chlorine and oxygen radius are similar in size. Magnesium is not changed. So the two things can have a difference. So in this case, distance does not change significantly, but the charge is much different. So oxygen having a +2 or actually having a -2 charge is going to have a much stronger interaction with magnesium, which has a +2 charge, than the chlorine will. So magnesium oxide is going to have a higher lattice energy due to those stronger interactions. It'll take more energy to break all those interactions and have a higher lattice energy than magnesium chloride. Lastly, let's see what happens when we put these two together. So we've looked at charge and distance. Well, what happens when we have two that differ in charge and distance? So here's sodium fluoride and magnesium iodide. So sodium is +1, fluorine is -1. Fluorine is very small, sodium is very small. We compare that to magnesium iodide. So iodide is much larger and -1. Magnesium is larger and +2. So we have a stronger charge, but they're further apart from each other in magnesium iodide. Sodium fluoride, we have smaller charges, but they're closer together. So which one will dominate? We can diagram it like this. And in these distances, for these distances, changing the charge has a much greater difference on lattice energy than changing the distance. So in this case, the magnesium iodide is going to have a much higher ionization energy than sodium fluoride, having twice as much charge, or available charge being twice as great, and magnesium iodide will lead to a much higher ionization energy. Due to the way the solid forms, and here representing the solid by 1s and 2s, you can imagine 1s being negative charges and 2s being positives if you like. And the way this is arranged, that if we were to shift it, we were to apply stress on the top and the bottom and shift it by one molecule, by one atom. Now we have, instead of in our original diagram having all of the positive charges surrounded by negative charges, now we have positive and negative charges adjacent to each other. So we have negative against negative and positive against next to a positive. And these will repulse each other and they'll try to get away. So if we shift it by one atom, it then breaks away from itself. And this leads for our ionic compounds to be brittle. Okay, so we know a few things about ionic compounds that have generally high, strong interactions. We know several things about that. They have strong interactions. They're brittle compounds, and we can characterize the interaction according to lattice energy. And lattice energy follows the same rules as everything else. It follows Coulomb's law, and the strength of the lattice energy is affected only by distance between the charges and the amount of charges. When in competition, the amount of charge dominates over the distance between charges.